The goal of this experiment is to determine the rate law for this iodine clock reaction. So the rate law is going to be your rate constant K, that's something you'll have to figure out with the right units, times the reactant I minus raised to the power A, so this is the order of the reaction. And that gets multiplied by the second reactant, S2O8 minus 2, this is called the persulfate ion. And that reactant is raised to the power B. So we have to find K, rate constant, with the right units. We have to find this exponent A, it's called the order of the reaction with respect to this reactant. And we got to find exponent B, the order of the reaction with respect to S2O8 minus 2. So the overall order of the reaction is A plus B. So this is the main reaction, but you will actually do a second reaction in the same test tube. So this will be, you'll do this in a test tube, not a beaker. In that same test tube, you're going to have this reaction that's also going to occur. So while this is the main reaction that you got to figure out the rate law for, there's a reasoning behind this so-called coupling reaction. Now, when you do this coupling reaction, you will produce a substance called S4O6 minus 2. Now, that reaction will take place inside this test tube until this S2O3 is gone. The S2O3 is the thiosulfate ion. So you will produce iodine, I2. The iodine in your test tube is going to react with S2O3 minus 2. Thiosulfate. The iodine will react with the thiosulfate to give you S4O6 minus. Now, the minute all of this thiosulfate S2O3 minus 2 is gone, the I2 builds up, and the I2 will react with the starch in your test tube to produce the blue color. So you see this reaction happens super fast, but the minute by having this coupling reaction, the minute all of this S2O3 is gone, the I2 will build up. The I2 will react with the starch and give you the blue color. So while we're not really concerned with this coupling reaction or the secondary reaction, the coupling reaction actually allows us to measure a good time, whether it's 2 minutes or 3 minutes or whatever time you get for each of the experiments. So you're going to do this 5 times. The first 3 are replicates, where you vary the concentration of each of the reactant. The fourth experiment is where you do this at a higher temperature, so about, I guess, 35 degrees or so. That should raise rate constant K. It should be a little bit higher, because if you raise the temperature, you increase the rate constant. And the fifth and final experiment you'll do is you'll do this reaction, but you'll add a couple of drops of copper sulfate. And the copper sulfate is a catalyst, so we would expect this rate, the time to go from colorless to a blue, to be very, very short. So catalysts will make the reaction go much, much faster. A couple of things here in terms of the pre-lab. What makes this reaction go? Well, if you increase the concentration of the reactants, the reaction rate will go faster. If you increase the temperature, the reaction rate will go faster. If you're talking about gases, if you increase the pressure, the reaction will go faster, though these are not gases. And if you add a catalyst like copper sulfate, the reaction will go faster. Concerning the pre-lab question, part F, so you have to remember, once all of this is gone, the I2 that's built up in your main reaction gives you the blue color. So to actually figure out the actual rate of how fast this reaction proceeds, you're actually going to use this, calculating the initial rate. You're going to use this formula. So the S2O3 minus 2, since there's 2 moles that's going to react in the secondary reaction, the actual time that you get where it turns blue is going to be not the rate of this divided by delta t, but the rate of this divided by 2 delta t. Here t is time, because you have 2 moles in the coupling reaction. So that's the answer to post-lab F. And you're going to use this to actually figure out the rates of all of your 5 experiments. So let's start looking at some of these post-lab questions. The first one asks to calculate the initial rates for 1, 2, and 3, these 3 experiments. So for that, you just go ahead and use this equation. So here's the data that we've gotten, and your data may be a little bit different, which is totally okay. Experiment 1, 2, and 3, we varied the concentration of the reactants. We did this twice, so you got an average. My temperature in the room was about 23 degrees when we did this experiment. And remember, the 4th experiment was done at a higher temperature. And then the 5th experiment was done when we added a couple of drops of copper sulfate, which served as the catalyst. So we're going to calculate the initial rates for 1, 2, and 3 using the averages. In order to do that, first we need to calculate the concentration of S2O3 minus 2 in each of these experiments. So let's go back to our data table, or more specifically our concentration table. So S2O3, we took 2 mils, and the bottle had a concentration of 0.010 molar. And so the concentration in this test tube is going to be 2 mils converted to liters times 0.010 molar divided by the total volume. Total volume in test tube 1 is 11 milliliters. So this is the amount of moles that are in the first test tube, and we take this and divide it by the volume in the test tube. And the volume of the test tube in experiment 1 was 11 mils. Actually, the volume in all of these experiments is going to be 11 mils. So realizing that the total volume in the test tube is 11 mils, I converted that to liters, so we get moles per liter. This is the concentration in test tube, the first test tube, which will be the same in test tube 2 and 3. The rate is going to be that concentration divided by 2 times our time, average time that it turned blue, and in my data it was about 131 seconds, so your data will be a little bit different. And I'm getting an initial rate for experiment 1, highlight that in red, as 6.94 times 10 to the minus 6 molar per second. So I'll highlight that in red. And that's how we will get the rate for both experiment 2 and experiment 3. So let's go ahead and follow the same procedure. We got the initial rate for experiment 1 and this value, and in green I went ahead and calculated the initial rate for experiment 2 given the time that we got for experiment 2. And this is the value that I received. Again, your data will be different. And for experiment 3, the time was 49 seconds according to my data. And doing that using this equation. So we already got a little bit of our data table here set up. We need to find the concentrations of I minus and S2O8 minus 2. So let's figure it out here. So go back to our table. So for I minus, we had 2 mils times a 0.20 molar solution. The total volume is 11 mils. By the way, the sodium and sodium are all spectator ions. So is the potassium K here. Those are spectator ions. So they're not going to do anything. Really, we're interested in the I minus here. So the I minus concentration is going to be 2 mils times 0.2 molar divided by 11 mils. So for experiment 1, we took 2 mils of a 0.2 moles per liter solution. The total volume was 0.011 liters or 11 mils, and this is the concentration we got for I minus. And we did the same thing with S2O8 minus 2, and this is the concentration we received. So these are the concentrations in experiment 1. Now if you look closely here, in experiment 2 we had the same volume, same concentration. The concentration is going to be the same as experiment 1, but in experiment 3 we doubled the volume, and everything else is the same. Total volume is still 11 mils, so we doubled the volume, kept the concentration the same, so the concentration is actually going to be double this. Looking at S2O8 minus 2, its concentration. Remember, S2O8 minus 2 is called the persulfate ion. Let's look at our table here. We doubled the volume, so keeping everything else the same, so it's going to be double the concentration. And then in experiment 3, let's look at our table. In experiment 3, we kept the volume the same as in experiment 1, leaving everything else the same. It should be the same concentration as in experiment 1. So now that we have our data table all set and ready to go, now we can calculate the rate law and finally get it into the form that's proper. Remember, the proper form is this. So our first goal is I arbitrarily chosen to compare 1 and 3, okay, or 1 and 2, but I'll do 1 and 3 first. So comparing these, remember rate is equal to K times the reactants, each raised to their order. So that's the rate law for experiment 1. The rate law for experiment 3, exactly the same. The only thing is the concentration. So let's start plugging stuff in. Rate 1 is going to be this rate in red. So I'll highlight rate 1 in red. And then rate 3 is going to be in blue. I'll highlight that one in blue. So let's plug stuff in and then see what we can get from there. So plugging everything in according to this data table, rate 1 is here, rate 3 is in the blue. The concentrations for rate 1, experiment 1, I got from here. Concentrations of rate 3, experiment 3 are shown here. Remember, I'm comparing experiment 1 and 3. Let's cancel out some stuff. So this whole thing here cancels. And the k's will cancel, though we're going to have to find k at the end of all of this. So we have 0.0364 divided by 0.0728. That's actually 1/2 to the power of a. So I kind of group the whole, you can take this fraction and group the whole thing under exponent a. So that's 1/2 to the power of a. Now this on my calculator, when I look it up, I'm getting a value of, so 0.3751 is what I'm getting when I solve this. This is a problem here. I'm going to have to try to solve for a. The only thing I can do is actually take the natural log of both sides of the equation. So when you take the natural log ln of both sides of the equation, you actually pop out this a. So natural log of 0.3754. So when you take the natural log of both sides, natural log of 1/2 to the power of a, by the natural log rules, the a actually goes back down to the ground. It actually takes it out of the exponent. So to solve for a, the order of the reaction with respect to reactant I minus, we're going to take natural log of 0.3751 divided by natural log of 0.5. Let's see what we get on our calculator. Doing that on my calculator, I'm getting an answer about 1.414. Now on an exam, at least my exam, A will be an easier number. It will either be 0, 1, or 2. But let's just go ahead, since these is not really, the data is kind of ugly, and actually real data, real science is really like this. So let's go ahead and just keep it at 1.414. So that's the order of the reaction with respect to I minus. To find B, I think we already compared 1 and 3. So let's compare 1 and 2 to find exponent B. So comparing experiment 1 and 2, here I have rate 2 in green. So green, 1.92 times 10 to the minus 5. So here's the concentrations for rate 1, experiment 1, concentrations for rate 2, experiment 2, the corresponding rates. Notice here the concentrations cancel out here, and putting in the concentrations and simplifying and grouping the bracket outwards, this whole thing is 1/2, all whole thing to the power of b. Doing this on my calculator, I'm getting a weird number, 0.36145. That's a problem. So to get rid of this, I'm going to take the natural log of both sides. When you take the natural log of both sides of the equation, just as we've done before, the exponent goes back down. And now I can just solve for b. And when I solve for b, order b, I'm getting 1.468. So that is the exponent for this reactant. All the way, let's go all the way up here. B is going to be 1.468. So we got our exponents A and B, the order of the reactions. So the overall order of this reaction is going to be 1.414 plus 1.468. But the post-lab question is asking for us to calculate K. So that's the last piece of the puzzle, and specifically that problem asks you to calculate K for experiment 1, 2, and 3 and get an average of it. So let's go ahead and do that. Be very careful. We want to make sure K has the right units, especially on an exam. You want to have K having its proper units because the units of K change. The value of K changes if you increase or decrease the temperature, but the units of K also change depending upon the experiment. I'm going to have my rate 1 for experiment 1 be in red. So solving for K here, taking all this stuff and dividing it out and isolating K, rate 1, let's go ahead and plug that in and plug in our values for I minus, its concentration, and S2O8, its concentrations. So plugging these values in and putting this in my calculator, this may be a little bit more cumbersome to deal with. Also, I want to address something about the units here. So with regards to units, I'm just going to round this up to 1. So remember, the brackets are moles per liter. So this will be moles per liter as the units. You cannot have moles to the power 1.4 divided by liters to the power 1.4. That does not make sense. So the units of this will be moles per liter, and units of this as well will be moles per liter because you cannot have moles to the power of 1.468. So to simplify our units in conveying them in terms of K, I'll just say this is moles per liter as the units, and this is moles per liter as the units. So how to do this on your calculator? So let's do this on let's just do this on the computer calculator. I'm going to start with actually, yours is going to be different. However you do it, it doesn't matter. But this is how I'll do it since I don't have a calculator ready right in front of me. I'm going to do 0.0364 to the power of 1.414. So 0.0364. My calculator is that little x to the y button to the power of 1.414. Okay, enter that. That's the value here. I'm going to times it. Okay, times it. Let's get my parentheses in here. Times 0.0364 to the power of this. So 0.0364 to the power of 1.468. Let's close those parentheses and let's hit the equal sign. So that's the answer there. And I'm going to need 6.94 times 10 to the minus 6 divided by this number. So dividing 6.94 times 10 to the minus 6, divided it by this product here, the denominator, I'm getting a value of about 0.0973. So that's good enough. So the whole thing in the math is 0.0973. We have m over seconds. This is big M. We just said we'll call this to the power of 1 in terms of units. And this is also big M in terms of units. So this M here is going to cancel out with one of the M's here. And the final answer in terms of our units is going to be 0.0973, 1 over M, 1 over seconds. So all of this m seconds. Now you can also write it as 0.0973 m to the power of minus 1 seconds to the power of minus 1. Both of these are correct. So we're going to do the exact same thing for K2 and K3, average K1, K2, and K3. So we got K1. Following the same procedures, we'll do it for K2. Here I have K2 in green. And I got pretty much the same answer when I calculated the exact same thing. Don't forget here, you're going to put the value of rate 2 and you're going to put the concentrations you got for experiment 2. So the concentrations I got here are 0.0364 and 0.078. So basically what I'm trying to tell you is make sure you plug in everything correctly. And then you also plug in everything correctly for calculating rate constant 3 for experiment. Plugging everything in, I'm getting in blue, green, and red, which is what we did together. They're pretty close. So getting the average, 0.073. M to the minus 1 seconds to the minus 1. I'll go ahead and let's highlight that. And times the concentrations to their respective power. So this is our final correct answer, and shown here. And let us bring it all the way down here, because this is really what you want to report on an exam or for this lab report. So this is our final answer. This next post-lab question is asking us to calculate the rate constant at the experiment at 35 degrees. So you did an experiment, the fourth one that was done at a little bit of a higher temperature. So when we did it, I got a value about 60 seconds. We only do this once, so you do not have to take an average. So let's figure out the rate constant. Now, if you remember, if you read back in your lab manual, the experiment 4 at the higher temperature was done at the exact same conditions as experiment 1. So I'm just going to shade this in gray to let you know that experiment 4 conditions, the one at the higher temperature, 35 or so degrees, has this was done under these same conditions. So we need to figure out the rate constant, rate equation to get the rate constant at 35 degrees C. So remember, this is the rate law, but we changed the temperature, so we're going to have a new rate constant K. So we got our rate here. So our rate is going to be 1.52 times 10 to the minus 5 at the elevated temperature. So our rate at the elevated temperature is 1.52 times 10 to the minus 5, so we'll plug that in here. The rate constant at this higher temperature is something we will need to calculate. The concentrations are the same as in experiment 1. So solving for K here, K is going to equal to the rate we got at the higher temperature, which we've calculated up here, okay, using this formula. Dividing it by all of this stuff here. Okay, these are the concentrations at experiment 4, which are the same conditions as experiment 1, so the same concentrations. And moving this all the way down to the denominator, isolating K, and doing this math, I'm getting a value of about 0.213 over m seconds, or you can say 0.213 m to the minus 1 seconds to the minus 1. The activation energy that we can calculate is from this equation. So we have a rate constant at temperature T1, and then we have a rate constant at a different temperature, T2. So here I'm going to compare K1, which was done at 23 degrees, and we will compare that to experiment 4, which was done at 35 degrees or whatever temperature you found it for. So here what we're going to do is we're going to solve for EA. R is a constant, and basically in this complicated math, what we'll do is we'll just try to isolate EA. First of all, let's plug in values here individually. So K1, I was able to get that's rate constant 1. So let's go all the way back up and see what rate constant 1 is. So that rate 1 is about 0.0793 with those units. And then K4, the second rate constant is done at a second temperature. We just calculated that. There we go, 0.213. So let's plug in those values in. Let's also plug in those temperatures in as well. So T4 is done at 35 degrees. The elevated temperature T1 is done at 23 degrees, I believe. 23 degrees. So convert them to Kelvin. R is a constant, and let's plug everything in. So plugging everything in here, remember our goal is to isolate and solve for activation energy, so I'll just highlight that in yellow. Let's do all of this stuff in math in our calculator. So I'll calculate this, subtraction, and I'll take that subtraction divided by 8.314, and then I should be able to isolate EA from here. So let's see if that holds true. So I took 0.0973 rate constant at one temperature, divided it by 0.213 rate constant at the higher temperature, take that fraction, and then I natural log that value. And I got this, minus 0.7835. I calculated this whole subtraction. Let me highlight that in green. I took that value and I divided it by this, the constant. I'll highlight that in blue. And I got minus 1.5832 times EA. So EA should just be minus 0.7835 divided by minus 1.583, basically solving for EA. So doing this on my calculator, notice the minuses cancel. Notice I'm getting about 49,482 joules per mole. You can also say it's 49.5 kilojoules per mole. That's also perfectly a right answer. So what is the effect of a catalyst copper sulfate? Well, you should automatically know that the temperatures, the time kind of went down um, for most of the reactions. Let's just compare the reaction rate with the catalyst, which we've calculated it to be about. Doing this on my calculator, the reaction rate is probably twice as fast. So here I'm comparing it with the first reaction. If you compare it with the second experiment reaction rate and the third reaction rate experiment, you'll probably get answers somewhere along the vicinity, about 1 to 2.5 times as fast. So the catalyst makes things faster. You probably have seen that and witnessed that firsthand.